study this is that we use ionic solution inside the capacitor. Imagine there's no gap, right? It's actually a gap here. This is S. So it's a potential difference. Not going to talk much about the electromotive force. We just take it for granted. We'll study more of this in chapter 7. So it starts with a potential difference of V here. So you have V and then here is 0. There's an electric field. Because of the electric field, we have mobile charges here. Charges of some density, and in an ionic solution you have plus charges and minus charges, right? This is the number density, so you multiply by the charge of electron. Okay. Also recall that from now on E is always 1.6 times the minus 19 coulomb. It is always plus. Okay, when I want to add an electron, then I'll put the minus E. Okay, just plus and minus here because I don't have to worry about minus signs. Okay, and what can happen here is because of the electric field, there is force on the charges, and you get an acceleration, and the acceleration is given by H7B Lecture F. I'm just going to look into orders of this magnitude here. I'm going to forget all the signs. Okay? So H7B Lecture is equal to dE over m. And if I just look at the velocity, because of the acceleration, then it's given by E times the electric field divided by m times time. Okay? But what happened here inside the solution is ionic charge is always colliding. Always colliding in the solution with a water molecule or whatever buffer you have. Okay. And the mean time between collision call it tau. Okay, so after some tau time, the molecule undergoes collision. It loses memory of its previous acceleration. Okay, so just imagine get accelerated for some time, average time tau, and then what happened is under collision, and then the molecule gets scattered. It loses memory of its previous velocity. Okay. So on average, then the velocity, the drift velocity due to the electric field then is given by, what's that, call it U, right? But that's just the average of the x dot. Right, and then it's just E times E over m times tau. Okay, and the current density in this case here is given by the positive, the density of the positive carrier times the E plus times the U plus. Okay. This is just the derivation of current density, the number density times the charge, the charge density times the velocity, and minus E minus E minus. Okay? And now I'm going to substitute the expression for U. And here I'm getting n plus E plus squared. This is part of the reason I don't worry about the sign, because the E will be squared in this case here, divided by mass of the positive carrier times tau, okay, plus tau plus here, n minus e minus squared over n minus tau minus times c. Okay. The most important lesson here is that not empirically or phenomenologically, the current density is proportional to the electric field. Okay. This is actually difficult to derive, difficult to evaluate, but from this model, from this simple model, phenomenological model. J is linearly proportional in E. Okay? And the constant of proportionality is given by sigma. Okay, this is called conductivity. I'm not going to define the unit for now. I'll refer to later in the lecture. And or you can also write it differently. Sometimes it's written as 1 over rho, that's E, right? And rho is called resistivity. Any questions before?
Yeah. When you had the drift velocity go to x dot, what did you
Say it again.
How did you get the drift velocity?
So what happened is this is an average property, right? So you have a bunch of mobile carrier, right, plus and minus. And on average, right, it gets accelerated by for a time tau, right? So it acquired a velocity that's linear in that time, right?
Oh, I see. I didn't.
Right, so what happened is, as I think I showed this last time, x dot, so it acquired this velocity over time, and then it gets scattered, right? It gets scattered and it gets scattered in any direction, right? So on average, after the scattering, it forgets of what happened before. It loses memory of its previous acceleration, so the average speed after the collision is 0. Right? So it does this, And on average, then the average drift velocity is given by an average over time, okay? And that is given just by this variable here, but we replace t with tau. And tau is the mean time between collision. Okay. And this is that. And this is the drift velocity, and the current density is the whole drift of this mobile carrier across the solution. Right, this is drift. And I guess Purcell or me, we're trying to be more careful here in distinguishing between a positive carrier and negative carrier. I mean, you can imagine, say, your solution only have one type of carrier.
Yeah.
In the case of solution, it's not true, but like in a metal or in a semiconductor, not in a semiconductor, in a metal or in an insulator, usually the carrier is just an electron.
Does the positive or negative affect?
Yes, that's a very good question, right? So if I have a positive carrier, right, the electric field will push it that way, right? It contributes to a current going this way. For a negative carrier, right, the electric field actually will accelerate it this way, right? But this also contributes to a current density going that way, right? Because the negative charge going that way is equal to like a current density going this way.
Yeah, so you end up adding rather than
Yes, you end up adding them.
Okay.
Right? So the plus charge going this way is equivalent to minus charge going that way. Keeping the same current density.
Is there a reason why you made because you originally had minus n minus e minus u minus in that equation, and you changed it to a plus between that?
Where? Yeah. Oh. This is just the carrier.
No, but like in between, like you originally wrote minus
Yeah.
the second term, but you changed it to a plus. the reason why?
Oh, you mean like from the last lecture, I put minus
Oh, I thought you wrote minus like 5 minutes ago. But
plus.
is there a reason why it's not minus? Because since you say the negative carrier is.
Yeah, well, it depends on, you know, whether I put a minus inside the E or outside the E. I put E minus here, so I'm just, you know, E minus here is minus E.
Okay.
Right. I just want to keep all the charges encapsulated within this index sign.
Okay.
So I don't have to worry about minus sign. Minus sign is the most notorious mistake you can make, right? It's always everywhere. So you just have to know how to take care of it a priori. But the physics is not confusing, right? Carrier times the drift, carrier times the drift, right? And they add, right? And the most important lesson, of course, here, this is a model. This is actually a very good model. Of course, you have to know what this is. To calculate that is not that easy, right? To know the density is easy, the charge is easy, the mass is not that hard, right? But the hardest part is to calculate the mean time between collision, or to actually measure, right? Or to calculate it from a theory, right? But the most important lesson is that the whole thing is linear in electric field, right? This is called ohmic material. As you can see, but let's go back to our discussion of the dynamic solution in capacitors. So you establish there is a potential difference V, this is 0, this is V, right? And then there's a current density, there's an electric field, there's a current density J, right? And this capacitor has area A, right? And the electric field is given by the potential difference by S, right? Okay? So I can define current. Remember, recall from what's over here before. Current is just, the total current is just integral of J dA, right? But in this case, J is constant throughout, right? It's just that linear in E, right? So this is just J times the area. Okay? And so J is equal to I over A, right? And then the electric field is given by that, right? So combining these two expressions, you know that J is equal to sigma E. Combining all these three expressions, what you have is I over A is equal to sigma V over S, right? Okay. And I don't know which one I'm going to use. Then V is just I times S A over sigma. Okay? And this is defined to be the resistance. R is given by S A sigma, or is also equal to S over A and so on. Units now. This part here. So recall that the unit of current I, which is just dq/dt, right? So it's Coulomb. It's Coulomb per second, right? And the unit of potential is volt. Is it volt or with an S or no S? No S, right? Volt. And so the unit of resistance, I'm going to actually volt per, and this is actually called ampere. Well, this seems very arbitrary. It's named after all these people. But what can you do? You have to just remember it, memorize it. If you, again, this is probably kind of pointless, but if you use a CGS unit, the unit makes a lot more sense, but we're throwing that away. Okay, and this unit is volt per ampere, right? And there's a name for it too, it's actually called ohm, right? Or a lot of times called that. Okay. Is this clear so far? Any question? How many of you have done circuits in high school? Okay, so you, from now on, things will be a bit more familiar.
Sorry, what's the difference between J and I?
Yes, J is current density. So if you look at the definition, current is JTA, so the unit of J is a square bracket, is denotes unit, right? The unit of J that is ampere per meter square. Okay. And just to continue on the unit, then the unit of, if you look at the definition of R, right? R is S over A times rho, right? Then the unit of rho, which is called resistivity, is inches ohm. Did I make a mistake? I think I made a mistake, right? Ohm per meter is ohm meter minus 1. I made a mistake. Okay. And the unit of sigma is the inverse of that. It's ohm meter minus 1. Right? Because sigma is just 1 over rho. And the reason we want to define this is because resistance is a concept, a definition that depends on size and shape. Okay? As you see from this definition, in particular for this kind of geometry, this is the geometry that we always use for lecture, right? Parallel plate capacitor, right? So you have an infinite slab separated by a thickness of an area A. So it's not infinite but large, and then the separation between the plate is S. Then the resistance has a unit of S over A times rho, right? So there's this depends on the shape, but resistivity is independent of shape. It's a property of material. So it's conductivity, depending on how you want to represent it.
This is like about the current density, but like you wrote it like as a vector, so
yes.
Like does that mean like it would point in the direction of
yes?
So,
it's like a flux, right?
So like I guess what confuses me is then like if you had like a circuit or something where the charge is flowing through and
yes.
like bent around, does that mean the current density is changing at every place because the direction is different?
No. It's a very good question, right? That's next. So I'll look into that. Any question up to this point?
You don't make any distinctions between sometimes the positive or the capital J's and lowercase j's. You're just using J.
Yeah, I'm just using J. I'm just using J. I guess it should be capital. No, usually it's just a lowercase J. Yeah.
It just looks like it's a capital when you put the.
Okay. Yes, okay. When I use complex imaginary number, I'm going to use I. And in electrical engineering, we use J. But physics always use I. Okay. We won't use complex number until much later in chapter 8
So
Yeah,
now
so that'll be
it's
like next
rho
week.
once we change that.
You know,
to
at the rate we're going.
Because we didn't use rho as
Oh,
like
yeah,
kind
but
of
there's
like
also another role.
Electric field.
How do we know?
Right, no, I was like, wait a second, those aren't the same variables as last week. Why did we change?
Yes, it's the same way.
Row
There are two kind of rows. So one row is resistivity. You have to know what you do an R here. Right. And then there is also a row for charge density.
Oh. So now
Wait, in the same
And then
context?
the same row.
I feel like it's
And it just
Wait,
have
so
to-
this row is 1 over sigma?
You know when you
Is
speak
the other
English,
one
sometimes
Q
the
over
word also
sigma?
depends on
Was that
context.
Q over sigma?
So it's a
The other
same
row,
way here.
charge density, is
I can't
that
help
Q
it.
Oh yeah,
over
it's the
sigma
same
E?
way.
Or is
But
epsilon?
Sigma is also surface charge density.
That's right.
I give up.
All these things.
Yeah.
Wait, so sigma for
So sigma is this sigma is conductivity, but it's also surface charge density.
Yeah.
How do you forget?
wow.
Then that somebody remind me. And rho is resistivity, but it also means
Okay.
volume density. Right? You just have to get used to it.
Okay, so what are you?
I can't
How
help
did you
it.
say that? to me?
Yeah. So
What is sigma?
now Nicholas has a question, right?
Conductivity.
So what happened when you have an object that is not shaped like that has a particular shape, right? In particular, it's very thin, it's very large, right? Area A, separation S, square root of A is much larger than S, right? So what happened in general cases, so usually, say you have a piece of wire, right? Or a piece of resistor, right? Usually, in fact, it's actually long, right? And L, area A, and the square root of A is actually much less than M, right? Say a piece of wire. Okay. But, so this is a conductor. So what happened here is, as you establish a potential difference, right, then you have an electric field in here, okay? And in theory, if you have nothing, you just have an electrode here, right? You establish a potential difference, 0 here, V here, right? Then as you know, this looks like a point charge, and the electric field is like that, right? Right? Imagine you have a minus Q here, plus Q here, right? So the electric field looks all over the place. Not all over the place, it looks just like the thing that's like guided, right? This is the electric field, okay? But in this case here, you actually have a material of a certain conductivity, and J is given by sigma minus E, right? And this has a property. In a steady state, divergence of J is equal to 0. Right? And this follows that the divergence of E is also 0, and this is true because, you know, from electrostatic, divergence of E is equal to rho over epsilon naught, right? But there is no rho here, the whole thing is neutral. Right? So what happened is that the conducting material that you have here modify the property of modify E. It brings all the E inside. Right? Then you have it here. So if I have two electrodes, all the E goes that way. Potential 0, potential B, right? And what you have is surface charges. Just remember conductors, we did conductors on last week, right? When you establish a potential difference, the charge will distribute itself. At some equilibrium, you have some charges here on the surface in such a way that all the electric field is confined in here. There's almost no electric field outside. Almost. Right? There's always fringe effect. Okay?
Well, I thought there was there was zero field in the conductor.
Perfect conductor.
Oh.
But in a perfect conductor, if you don't establish current, right? If you somehow establish current, that's electrostatic, right? That's really static where nothing changes with nothing moves. Here we're in a situation where things are moving, right? It's a steady state. It doesn't, on average, globally, nothing changes with time, right? But you have current moving, right? So when the current is moving, there's electric field. Okay. But in this case here, the property is modified from a situation that looks like a dipole here. Because of the current, you have potential, your equipotential surface will be like this. Right? And the electric field will always be along the wire. Right? Also, inside this conductor, this is always true. Right? So this is only possible if the current density everywhere is the same. Right? So the current density J is actually independent of cross-section of its position along the wire. Because E and J are proportional. And the only way to satisfy this, the only way to satisfy this line integral is equal to 0, is that the J has to be the same everywhere. If the J is not the same, then when we do this integral, it's no longer 0. We can talk more about this tomorrow and more discussion.
Yeah, I mean, I think we was getting at, if J is a vector, then like there's a bend in the wire.
Yes, yes.
Then is the direction of
Oh.
right. It's just like that's
Right. That's technicality, right? Meaning that, yeah, sure, then straighten the wire. Meaning that, just like, a cylinder, the curvature of a cylinder, at least along this direction, doesn't get changed as you bend a piece of paper, right, and a cylinder, right? No, I don't want to use that example, but no, it will be clear. What matters is that, it doesn't matter whether you bend the wire, right? As you bend the wire, of course, the current density changes. But often what matters is the current, and the current is still the same. I don't know if I answered that question very well, right? But you will not encounter any problem when you're solving a circuit problem. Okay, so where am I here? So with that in mind, we have everything that we need to talk about circuit. Okay. That kind of conclude our discussion on conductivity and resistivity. Right? So diagrammatically, so I don't have to worry about shapes anymore, right? I just know that a piece of material has a certain resistance R. Then if I can establish a potential difference V, right? This is a piece of material with resistance R. Okay. Then current will flow, I, right? And I is just V over R, right? But this is the potential difference. Suppose this is 0, this is V, okay? And I'm gonna be cavalier from now on. We won't talk about battery and electromotive force for a while, but just pretend that there is a way for you to actually move charges physically, mechanically, or whatever means that you have at your disposal to move a charge from low potential to high potential, right? And call that your battery, right? And the symbol is always that, right? So you feel like E, but I don't like that, but I call it V. So it's here's 0, here's V, right? And V is just IR, right?
so if charge is moving from low to high potential, the current is going from high to low.
Yeah, the current, so what happened in here is the magic, right? What happened inside
Oh,
the battery, right?
okay.
Inside the battery,
Inside the battery.
there's a little demon, right? There's a little demon that moves charges.
From
From
the
flow
0 to B, and then they flow around.
As far as we're concerned right now, there is the little demon, right? I'm not worried about the mechanism for it yet, but because we don't have the conceptual understanding of a battery and electromotive force for a while. So think of a demon that can move charges, positive charges, by the way, right? So we're not worried so much yet about whether charges are electron or positive charges. For the purpose of this, see, that's why I call it diagrammatically, right? Charges is always positive charges, right? So when I write a current like that, that means I have a positive charge flowing in that direction, right? So at some point the positive charge gets over here, and the demon has to bring it up again, right? And the battery is the demon, okay? And V is IR. I is V over R, they're all the same thing. Okay, so an important concept to remember is actually, that can be very useful, is what's called voltage drop. If I have a resistor, R, right? And there is a current flowing through it, I, right? Let's call this point A, point B. There is no demon here, okay? Then the voltage drop across is I R, right? And this is the voltage drop is this is also diagrammatically only for the purpose of analyzing the diagram, right? You don't care so much about reading what's happening, okay? If you pretend that there is a current going that way, even though it might not be happening that way, right? Pretend there is a current going that way, there is a resistor, right? Then pretend that there is a voltage drop, IR, across A and B, and it's higher here, plus here. So it's a positive, in this case it's a positive voltage drop. This will be very useful in analyzing circuit. Okay? So let's look at an example. Well, I don't want to put an example yet because the example will be pretty simple. Right? Just like this, right? This is okay, this is the first example. But before I do the examples, there are two more concepts that we need to know. But you already knew about this. First of all, is concentration of charge. So if I have a fork, if I have a branch like this, right? If I define I1 going this way, right? And I2 going that way, I3 going this way, right? Then concentration of charge tells me that I1 has to be equal to I2 plus I3, right? Or any network you want, right? So in all generalities, of course, you have. Let me change this. 2, 3, but in general, if I have a current all flowing in a node, I1, I2, Ij, In, right? Then the sum of Ij, j from 1 to n is to be equal to 0. Right? You cannot just have an accumulation of charge over here. What comes in must get out. Okay? That's just that. It's just a concept of change charge. The second concept is also you already know about this. Right? So there's really nothing new about circuits, right? It's all just applying for electronics. The other concept is this. right? The line integral of E along the loop is always 0, right? So if I have a loop, right, with a lot of elements, one, two, three, four, and so on, right? And I know you just learned about the concept of voltage drop, right? Then the sum of all the voltage drop, right, from I equal to 1 to n, has to be equal to 0 also. Okay? Just have to be careful about the demon, right? The demon has the opposite sign. The demon moves charge from low potential to high potential. Okay?
So when you say voltage drop, like, so does that mean that the charge is, or the voltage is V and then it goes to 0? Like, if it's a
No, meaning that there's a difference. There's a difference from A to B. The difference is given by I times R.
But if it starts out at IR, so like,
Right, meaning that the difference in voltage between here and here is IR. If I define current equally that way,
so is it like 2 IR on the other side, or is it like 0?
you'll see it with the example. Can I do an example again here? Okay. So let's do a simple example. Simple example is your battery and this is the right? And again, with circuits, you define a lot of your convention, right? There's a battery and there is a current I, there is a R, right? Here in this case there is no branch, so you don't have to worry about the first concept, right? The concept of voltage drop, right? So you just trace it along, right? Along here there is a drop of I'm not very good at this. Usually I just do it differently. But the idea is that there's a drop here which is equal to minus IR, right? Higher to lower, right? But then there is an increase here, right? And then you have a plus V. This is the second concept. Right? And that has to be equal to 0. I'm just tracing around the circuit, right? There's a drop and there's an increase, right? It's as simple as that. If I think of this as a potential landscape, right? You know, like just in a rolling hill, right? And when you want to get back to the same place, right? Then the sum of all the potential eventually becomes 0, right? So you go down and then you go up again, right? It has to be equal to 0. So V is equal to IR. And there's a name for this. This is Kirchhoff's law. This is a very famous physicist from Germany in the late 1900s. This is Kirchhoff's law. This is the second one. This is also Kirchhoff. This is number 1. But there is no more than just conservation of charge. And then the line integral of E is 0.
So does that mean along the wire between the resistor and the battery, the voltage is 0?
Yeah, we're assuming in this case diagrammatically, this wire here is superconducting, right? There is no resistance, right? But this is just